Linkage, I guess that I have to introduce both of you. He's been, I don't know how many years you've worked there, but he's done a lot of work in various aspects of record linkage, from string comparisons to statistical estimates to very large-scale high-performance record linkage. So there's lots of knowledge about how to link very, very large databases. It's my pleasure to have you here. Thanks for coming.
Thanks, Peter and Chris, for the invitation. I'm going to talk about some of the computational methods for cleaning and linking national files. The methods actually begin with theory, and I'll say something about that. And my original abstract just talks about the record linkage, but I want to put that in the context of where we're cleaning up data, we're doing our linkages, and then we're going to try to actually do some statistical analyses on the data. And at least this fifth topic here is been open for about 51 years. There's about 15 papers, and I'll say something about that. So our initial goals when we analyze a bunch of data is to bring together data from different sources, and then if you were, say, an econometrician, you might want to create a econometric model for energy use. If you're dealing with the health of individuals, you'd like to combine a lot of data from different sources. Typically, we can use name, address, and date of birth. Sometimes there's other data. And as people mentioned, it's very typical for about 10% or even more of the addresses to change every year. So that's problematic if you start using one list that's 3 or more years old. The idea, though, of combining things is to actually analyze the A data against the B data. So our issues are going to be, we want to clean up the original data in each of these source files, and you're going to have missing data, you're going to have contradictory situations. For instance, you want to impute things in a manner that preserves joint distributions. You don't want to impute somebody that's like under 16 years of age and married. You want to get rid of the duplicates in your original sources. Maybe you want to deal with coverage issues. Then what we want to do is, is to unduplicate in each of our source files. And we create a merged file, and then at some point we want to do a statistical analysis on the merged file. And the issue with the merged file is, if you have 1% error, maybe it's okay. If you have 5% error, maybe you can do a few analyses. If you have 10 or 15% error, then it's questionable what analyses you could do. And there's been some enhancements, and I'll talk about that. The things that I've done mostly in about the last 10 years is because of what the big types of files we have at the Census Bureau. We want to increase the computational speed, sometimes by 2 to 6 orders of magnitude. So at that point, we can do sets of national files. So our cautions, we have 5% error in each of the files A and B. We have 5% matching error. The errors are typically additive. So we'd have 15% error in this data here. Are there any analyses that are possible? If we reduce the error, then what analyses are possible? It's very likely some analyses are possible with 5% error. I don't quite know what those are yet. And how will we even know how much error is in the files? One of the big problems is if you give people access to data, they're not going to be able to figure out that, wait a minute, we have 10% duplicates in these files. You typically use name and address information for that. You can tell if there's missing data But now if you have to go to the subject matter experts for the edit rules, like a child under 16 not married, you're going to have to do a considerable amount of cleanup of the files. So a lot of leading statisticians over the years have assumed that there was no matching error when files were linked. So this is an example from sampling. This is Journal of American Statistical Association. And they assumed that there was no matching, but unfortunately, matching error. But if you have matching error, then you could have a 5 to 10-fold increase in the bias and variation of the estimates. Steve Feinberg and other leading statisticians originally assumed that you do not need to deal with the linkage error, but of course he's had a number of very good students the last few years that have worked on the record linkage problem. And if we have the error in the linkage, then that affects a lot of the things we want to do with the data. So it could affect what's called adaptive design, capture, recapture, which a number of you have done, and the sampling and estimation that I just mentioned. And again, if there's 10% error, then what analyses can you do? So with edit imputation, the goal is to fill in the missing data in a manner that preserves joint distributions and remove contradictory data while preserving joint distributions. And over about the last 35 years, 5 statistical agencies in the world have been able to develop these systems. They use what's called the Flagy-Holt model of statistical data editing, and things were a little bit slow to implement because Flagy and Holt rediscovered one of the fundamental problems in logic programming. So you need integer programming, set covering algorithms, logic programming, and satisfiability. So these would be like our edit rules, and we have to have efficient ways of putting these together and using them in these models. Child under 16 cannot be married, structural 0, in a contingency table for log linear modeling. Each generation should be separated by at least 15 years within a household. Child under 16 and in school cannot be part of the labor force. So in '97, I did some set covering algorithms for initial version of the software that were at least 100 times as fast, but possibly 1,000 times faster than what IBM had developed for the Italian labor force survey. And I actually got their data. The Italians sent it to me because it's just logic restraints. It's not actual Italian data. Agnes Boskowitz at Australian National University in 2008 generalized my theorem, and her proof of the main theorem was almost 200 pages long. Ton de Waal from the Netherlands and I were the outside reviewers of her PhD thesis. In 2003, I showed how to connect editing with modern imputation. And the key thing was that if you have the implicit edits a priori, you can build structures in just the right fashion so you can embed your imputation modeling into that. In 2008, I discovered, using some work on statistical matching that the Italians at ESTAT had done, I used some of their data, and I realized it was possible to speed up the conventional algorithms by like a factor of 100 or even 1,000. Used convex constraints, which was in one of the Annals of Probability papers I had, a generalization of the ECM algorithm of Meng and Rubin dealing with missing data. And we were actually able to use it to generate synthetic data. And I teach a short 2-day or a 1-day course on modeling edit imputation. And the methods are suitable for junior analysts and programmers to produce good models. So there's promising new research relates to connecting editing with Bayesian imputation. And I list a whole bunch of papers. The common thread here is Jerry Ryder at Duke University. the most recent paper is probably going to appear in JASA sometime in the next 6 months or so. They use MC-MC methods that are about 2,000 times slower than what I have, but they are superior in terms of the quality of the things that they're producing. They need somebody in OR to come in and develop faster algorithms than the MC-MC algorithms that they're currently using. Now, for record linkage, a number of you that have worked with it have known over the years that that can produce a lot of efficiency. The first problem at the Census Bureau I was asked to work on was called the post-enumeration survey. And what we did is an independent enumeration of the entire US, at least a sample of blocks. It was matched against a sample of blocks in the census. And Howard Hogan and Kirk Walter, who initially developed the procedures, there were 7 components to it, thought that there might be, you need 3,000 individuals in 6 months to do the clerical matching. And it needed it, they thought the matching error rate would be about 5%, but their model required at most a matching error rate of 0.5%. So there was an article by David Friedman from Berkeley in the New York Times op-ed article that said he thought it was impossible to do matching with this type of accuracy, with the type of time constraints that we had. So we developed that system and tested it in 1988. We did get our desired error rate, and the time was fine, because we had to do the entire United States in 6 weeks with the type of computers we had about a little over 20 years ago. Well, we did some refinements in our methods, and we were actually able to reduce the error rate and still use the same amount of time. And of course, the clerical review was drastically reduced, which not only saves us time, but obviously money. So the thing that was unique in our census was that we had to develop optimal parameters for 500 different regions. So it was unsupervised learning. And as far as I know, this is the first time that was done. I gave a talk at one of the knowledge discovery conferences back a number of years ago. Stuart Russell was the other invited speaker, and I mentioned that everything we had to do was unsupervised, and the machine learning people didn't believe that that was possible. But our stuff has been validated. In other words, people have come in and independently reviewed it. We had to deal with typographical error, which you've heard about, Smith versus Smoth and whatever, and then I showed how to combine that with the likelihood ratios, which I'll talk about in a minute. Flagey and Sunter, as people have mentioned already, developed a theoretical model. And Howard Newcomb actually introduced the ideas, but he didn't have some of the theoretical ability that they had. And so they introduced this model. They look at likelihood ratios over patterns of pairs. And they divide the pairs into matches and what they call non-matches. This is their notation. And the gammas can be agreement patterns or partial agreement patterns or things that use frequencies and whatever. And you look at a likelihood ratio like this, and if you have a bunch of agreements, that happens more often among matches, and so this gets larger. And if you have mostly non-matches, disagreements on these identifiers, that usually happens more often on the non-matches, so the denominator is smaller. So it gives you a natural rule, and the natural rule is that if you're above a certain point, you designate the pair as a link. Below a certain point, it's a non-link. And then you have an in-between region where you hold things for clerical review. And their theory was that if you put upper bounds on the error rates you accept in the first and third region, their procedure is optimal in the sense that it minimizes this in-between region. It was based on hypothesis testing. The rule's been rediscovered in the information retrieval information, Cooper and Marin from Berkeley, but without proofs of optimality. And our difficulty was that we had these 500 regions, and there's additional difficulties here. So our automatic parameter estimation, this would be like matches. We're taking what's called that weight, which is the frequency ratio, or like a natural logarithm of it, and plotting it against the frequency of these observed patterns. We have this in-between region where we decide if something's a match or a non-match. In our decennial census, in all 500 regions, this consisted primarily of people within the same household that were missing both first name and age. So the only way we could do the clerical resolution or whatever is to do some sort of follow-up. There was no information to do it automatically. So the types of curves we get, this might be a decennial census, where the curves separate quite a bit. This could be a poor quality population list or administrative list. This could be even poorer quality. Over here we could have like agriculture lists, which I worked with. And over here it could actually be general business lists, but I'll say something about that later. So the types of pairs we might see, this would be an easy thing. We brought things together. Somebody could look at it and say, well, that's probably a match. And you can see the A and H differ, but that could be like where somebody couldn't read the handwriting or whatever. The next one is more complicated, but you could have like an Anglo enumerator that went out and got things by hand and didn't know how to spell Javier Martinez, and so that was their spelling. You needed some way to deal with that. You can see there's some typos in the words here, and the ages differ by a little bit more. In extreme cases, but something we might do in certain situations, we have a Jillian Jones who is like a medical student at the University of Michigan 20 years ago. And the Jillian Brown is from a list of physicians living in the Detroit area who are known to have attended the University of Michigan Medical School. And so you could do some follow-up, but that would be a more difficult situation. We need to standardize addresses, and the idea is to break it up here. No, this would be names first. And this was something we developed for our agriculture census, but we've also used it for business lists and for person lists. We need to standardize addresses, and our main address standardizer breaks things up into 80 components. I'm only showing this much. And then we worked on these things for a number of years, so our name standardizer and our address standardizer, and we did extensive testing in 1994, and these were substantially outperforming any of the commercial software that we had access to. There's been more advanced things using, in the first, hidden Markov models. This was a two-stage Viterbi algorithm. Peter Christen and his colleagues did it with a one-stage Viterbi, and they actually showed how to develop your training data without training data, and it was a very practical way of doing it. Egenstein and Ganti and Cohen and Sarawaji developed more advanced methods, but I don't know if they've actually been implemented. There were plans out at Microsoft Research to implement some of these ideas, but that was around 2004, and I don't think they were ever implemented. String comparators to deal with string comparison. You've heard about the edit distance. There's something called the Jaro-Winkler string comparator. I showed how to combine that with the likelihood ratios. William Cohen and his colleagues at Carnegie Mellon did two big studies of string comparison. They concluded that what he actually named it the Jaro-Winkler string comparator, and he felt that it was about 10 times as fast to compute as edit distance and worked almost as well. We've used it with census data and some other data, and it works as well as edit distance on certain data, but not in general. These would be the values of the string comparator. They're scaled between 0 and 1. Here's your edit distance. Everything was transformed so they're on the same scale. And you've already heard a little bit about bigrams and trigrams in terms of the confidentiality things. What happens is that with our data that we had at this particular time, if we couldn't have dealt with typographical error automatically, we would have lost 25% of the matches. Another extreme situation, in our decennial census, we can't find everybody, and here's an example. We occasionally can bring people together in a household, and this would be like a single mother with some children. Maybe this form was filled out, and this was like some sort of follow-up form where a neighbor was interviewed. And the interviewer assumed that the children had the same last name, but what had happened is the woman had gone back to using her maiden name. So what I can observe here is that there's no 3 grams in common, and we can't get these, not without the existing sources, although we could do auxiliary sources. So at a minimum we lose on the order of 0.5%, and I already showed you the other 2% where we're missing both names and addresses of people within the same household. So for our decennial census, we developed something called big batch technology software, and I'll say more about that in a couple minutes. I had some blocking criteria, as they're called, that I developed in 2004. We had 3 people at the Census Bureau that independently came up with better blocking criteria than I had developed. So they're the ones that developed our blocking criteria for the 2010 census. The software is very fast. For the software that was available in 2010, our software was 50 times as fast as prototype parallel software from the computer scientists at Stanford. And I still believe it's 10 times as fast as software that's recently come out. It's parallel software. We do detailed computation on 10 to the 12th pairs out of 10 to the 17th. It took us about 30 hours using 40 CPUs on an SGI Linux box. This machine had 2006 Itanium chips, so all your machines nowadays would probably be at least 4 times as fast. So generally, if we could do this much, say approximately 10 years ago, you should be able to do better now. What was interesting, I made some changes in one version of the software in 2009. The lady who I'd worked with very closely for over 20 years said that if the software was any slower, we couldn't use it for the decennial. And this is talking about software at the time that was 50 times as fast as any other software I knew about, just about in the entire world. The big batch technology, we introduced that. We actually wrote the first code around the fall of 2000, but it was about 2 years before we had something we thought was ready for preliminary production testing. Our decennial area tested it extensively. They asked us to do a lot of modifications that made it easier to use in a production environment. There are some advantages to this. We can use lots of blocking criteria. There's no sorting of files. New indexing. We're using sort algorithms, but only in a certain sense on things that we keep in memory in a certain way, and I'll explain that. We only make 1 pass on each file. So with conventional record linkage, you'll do a whole bunch of passes and you'll do a whole bunch of sorts of the files. So the small in-memory file A, and ours was naturally divided, the whole US is divided into 500 regions, but you can do it with administrative lists or other lists. Break it up into components. The idea is the small components you want to fit in memory. For each blocking criteria, we create two indices. One, this corresponds to the sort order, but it's done in memory, so it's very fast. And this one is for the almost instantaneous retrieval and comparison of the records. Bill Yancey developed that, and it must be close to 3 times as fast as anything that we were aware of in the computer science literature. In 2001, when we did our preliminary testing on just standard PCs, which are pretty slow by today's standards, we were doing everything, but it maintained a steady 100,000 pairs per second in terms of the matching. During the Decennial Census in 2010, we maintained a speed of about 400,000 pairs, and with the new servers, it would be at least 900,000 pairs per second. Okay, or let's say a PC that's sitting, if you have a Core i7 or a Core i5 machine at home or in your office, that's the speed you would get. The software is completely portable across all machines, including IBM mainframes, Macintoshes, or all the machines that the Bureau uses. We have very significant savings in times of disk space and also the skilled person intervention. Programmers, or even moderately good ones, are a limited quantity, and this greatly reduces all the things that they have to keep track of. Just in the, 15 years ago, just the sorts of the files would have taken just days. I'll go back here. So if we had a billion record file, then several sorts, each sort could take like half a day. So we might spend just 5 days on the sorts of the files. We're concerned about error rates, and we want to do that without training data, and I'll say a little bit more about that in a minute. Bellin and Rubin did the first unsupervised learning thing. I did some generalizations in 2006, and Peter Christen had some other things. For false non-match rates, I had some things. Hall and Feinberg gave something, but it might not be computationally tractable. In other words, it may be like 10 orders of magnitude too slow right now. But it looks like it had some nice ideas. With our parameter estimation that we were using in 1990, we were in the midst of production. We had 3 specific areas that we were matching. The programmers I was working with said, the clerical review blew up in these 3 regions. What's coming off? So I went in to look at it, and what we discovered was that 2 of the keyers had bypassed the key punch edits. So every record that they keyed disagreed on age within a household. And our EM methods automatically picked that up. That's unsupervised learning, but we still dealt with extreme typographical error that was induced by 2 keyers. And then, of course, the big problems are in this in-between region where you don't have enough information to make a valid decision. So for our parameter estimation, I'll talk about what's called semi-supervised learning, but generally we used where you have a little bit of training data to combine with what's called unlabeled data. But most of our methods are for unsupervised learning. I had the Nigam et al. Paper about a year or a year and a half before it appeared. I did some generalizations of it using some of our record linkage techniques. The key feature was that I was able to generalize boosting to improving the parameters in a model to simultaneously improving the model and the parameters. During the research, I discovered that the guys from Bell Labs had earlier looking at all pairs of words, and later the guys at Microsoft Research had looked at all triples of words, each case concluding too much noise was added. I used our record linkage things and some set covering algorithms and discovered that I could pick out about 80,000 pairs and triples of words out of 120 million to get the improvements. Larson and Rubin did the semi-supervised learning, and then I did a generalization of it. They used full MCMC, but the EM methods that were almost as good in terms of quality were a lot faster. This is our model, and this is a standard statistical mixture model. We have classes. We might have 2, we might have 3 or more. And the theta just refers to parameters. And the gamma would be like agreement on first name, last name, and so on. And we're making what's called a conditional independence assumption. We use a Dirichlet prior. All these things are standard in psychology, economics, statistics, and machine learning. This is a representation of the likelihood. The lambda would be a weighting between 0 and 1 between what's called the unlabeled data. So if lambda is actually equals 0, this was our standard unsupervised learning. The z is an indicator of whether or not it's a true match or not. And then with labeled data, which people traditionally use, you just can kind of add things up and quickly get your parameters. So we use some of these ideas. My 88 paper, what we used for the parameter estimation during production, finds the best general approximation, this naive Bayes of a general interaction model. And I have a couple papers that give details on that. It's been rediscovered by Kim Larson in the machine learning literature, but he used general additive models, which are much slower to compute. So these are some comparisons here. The first column would be the final methods I had. And let me give here, instead of showing the types of curves that pull apart like this, I'm only plotting the bottom 10% of the tails, and this is accumulation of the estimates against the truth. The closer you are to the 45-degree line, the better your estimations are. And the problem, the reason I didn't use the 2-curve thing, which has been typically used, is it makes it look like you're doing too well. And here, if you look at these a little bit carefully, you're doing okay, but not super great. This is the Bell and Rubin stuff, and this is the semi-supervised stuff that Larson and Rubin and I used. And you can see, obviously, semi-supervised is doing the best, because what you do is you concentrate your sample of truth pairs right around the upper cutoff, and that gives you the improvement. And the problem is, in one region where we have all these blanks that I talked about, 1 out of 40 might actually be a true match. And that would be like in a suburban region where we have higher quality data. In an urban region where we have lower quality data, more missing, more typo, it might only be 1 out of 10. And I don't see any way to do that unless you have some a priori information. Now, adjusting analyses for linkage error, this problem's been around for a long time. Particularly the last couple years, there's been quite a bit of good work. I guess Katie Heron's been involved with a little bit of the work here. Hoff and Zwinderman at the University of Amsterdam. Some of the work I really like is, let's see, Tancredi and Liceo here give a full Bayesian thing. And then one of Don Rubin's students did, and some of his colleagues at Harvard at the time, gave another approach. But I'll say something about this, give you some background. We start out with a couple files, there's linkage error. And the idea is we want to bring together X and Y data, and X and Y can both be univariate. Instead of observing Y, we observe Z sub I. And sometimes it's correctly matched, and other times it's incorrectly matched. And then, of course, the probabilities have to add up to 1. So we want to adjust this analysis for the linkage error. And here is just our we're saying if we knew the truth underlying things. We force 1-to-1 matching, which you don't have to do. We're just saying you either match to one or the other. And we actually have a bias adjustment if we can estimate the PI and maybe the set of the QJs. So here are the situations where we're doing this matching. And what Lahari and Larson in the JASA paper did, they gave the full development here and showed how well their methods work. So theirs expanded on what we did, except they didn't have methods to get the PIs and the QIJs. We used Bell and Rubin for that, or we could use some other methods, but there aren't many out there right now. So the types of curves we could deal with, here we could get the error down to about 1%. We didn't think we needed to use the adjustment. Here it worked real well. Here the adjustment procedure worked well if we could estimate the underlying probabilities, but at the time the Bell and Rubin procedures wouldn't work because there's too much overlap of these curves. And this is with our business list, but we'll have to show something in a minute for that. So our regression coefficients, we have the matching weight, and as the matching weight decreases, we get more pairs. So with our observed data, the regression coefficients decrease because we have too much bias thrown in because of the matching error, and the adjustment makes it look like this. If we have the estimated true probabilities, we can get it look even better. This was with what Shuren and I did with 2 ad hoc adjustments. With the Lahari Larson, they actually got something that was much closer to this horizontal line. But here, the points are from the estimated regression coefficient against the true one. And so as you get progressively biased below, it drops below 1. Later, we thought we'd do some analytic linking. This has been taken much farther by later work with people that had better skills. We were just using basic EM things, but I think you need full MC methods. We do our record linkage. We'd have our X, Y, and for high weight pairs, in other words, where the error rate is lower, we could build a model. And the idea was if something was an outlier, according to some regression criteria, we would replace the existing thing that we had put in with its predicted value according to the model. So we had this name and address information, but now we have like an X and a Y, and we have a model that gives us like a predicted X or a predicted Y. You could do it either way. So you have an extra piece of information that should improve your matching. So the situation with all pairs is like this. We're able to, when we look at all pairs, we have this type of situation. So you can see it's very hard. So the regression, the R squared drops from about 0.4 down to 0.07. So you really can't analyze this data. So we got our model using the high weighted pairs. We put in these predictors and we redid the matching, and this is what it looks like. So it goes from this to this. And you can see that you can sort of tell that you've improved the matching. So you get rid of about 3/4 of the matching error just with that one step. Now that's been redone, but in the more recent work, this is Gutman et al., Goldstein et al., or the recent things with Tancredi and Lucio, they were using R squareds of about 0.7. And you start getting in a little bit of trouble down about 0.4 on your R squared, and if you go all the way down to 0.2, you can't do it at all. So there's going to be a bunch of future work. So the Gutman et al. Did it just called statistical matching, but it still applies to things that everybody else has done. Chipperfield et al. Do it with discrete data. not like a regression situation, but it gives some good insight into what's going on. And then the Goldstein et al. Work gives ways to do the adjustments, and then the work by Tancredi and Lucio. And I won't go through this part. So the concluding remarks, we want to do our modeling edit imputation, and that's part of our cleanup of the original files. And the methods for that are pretty mature now, meaning that there's software out there and people understand a lot of the methods. We want to unduplicate within a file, and then we want to merge across. But those technologies are pretty mature now, and we've seen a lot of good examples today. Now, to adjust statistical analyses for linkage error, there's been 15 papers in 51 years, and I believe the problem's been about 5 to 10% solved. So there's a lot of work that's still needed. In terms of speed, we have generalized software for at least edit imputation and record linkage. Skilled team, exceptionally fast software. 3 to 6 months, we can do the cleanup and preliminary analysis of a set of national files. If you use software that's 100 to 1,000 times as slow, it's not clear how long the work would take. So the speed of computation really makes a big difference. Okay? And that's it for this talk. Thank you.
Great, thanks very much, Bill, for a very broad-ranging talk. Any questions? Sorry.
Harvey Goldstein. Thanks for that, Bill. It seems to me that I think actually more of the problem's being solved than 5 to 10%, but leaving that aside, it seems to be one of the big issues is where your linkage errors are non-random. They're associated with the variables you're going to use in your model of interest. And I think that's a really serious problem.
We've looked at both cases.
I just really wanted to ask you where you think the future of that is.
I think you're going to have to deal with it where the linkage errors are, say, correlated with the some of your data. Deal with that separately. We looked at some age things originally, and we did have some correlations there. That was Fritz Schurn and I back around 1991, though. But we didn't follow up on that, because most of what we looked at, we didn't have those correlations, but it might have just been because of the types of data we had. Or the correlations weren't quite as severe, and so we didn't think we needed to deal with it at that time.
I think some of the medical literature, for example, suggests that, for example, names, difficult to spell names, are associated with particular ethnic groups or social groups and so on. And you can actually reverse your inferences if you're not careful. And there's, I think, increasing evidence.
Yeah, I agree with that. I strongly agree with that you're going to get certain subgroups, or we've had the situation where in urban areas we couldn't match the people as well because there's a lot more errors in their data and missing data, and they had distinctly different characteristics than the people in the suburban areas, and so we had to worry about it. And it's not like we did anything much about it, but both Fritz Schurn and I had been in places where people worried about that. Yeah, Nancy.
There seems to be a debate about these adjusting for linkage errors. So in some of the literature you read that they use the matching probabilities of the parameters that were estimated to adjust for the linkage errors. And in Chipperfield in particular in the ABS, you see that they're actually using some small sampling to get error rates. So what is your view on that? Sort of, should we be looking at the probability of being an error, or can we use the match probabilities to adjust our?
The match probabilities, generally people haven't been able to estimate accurate ones without training data. And in our case, like we'd have 500 regions where we have to do that. I mean, we could probably approximate based on clusters of regions. But we simply weren't able to estimate the underlying match probabilities. And what I didn't show here, but I'll just state, with the Bellin-Rubin stuff that we looked at very carefully, because Tom Bellin was on my staff for a while, And then later with what Larson and them and I did, and Larson was on my staff also, those estimates aren't very accurate. And unless the estimates are sufficiently accurate, a lot of these adjustment procedures don't work that well. The new things that use the very heavy-duty Markov chain Monte Carlo, I think are ultimately going to give how to do it. Now, what they're doing is, in what the recent Tancredi and Liceo paper, which is December 2015, do, they show how you have some matching error and you get some initial idea, and as you go along you get a better idea of what your model looks like. And so when your things you are imputing or putting in there differ from that model more, you also reduce the matching weight, and it's all done automatically in their thing. In their paper at least, although it's hard to pick up in it, they're the ones that explain that the best right now, because they've been through it for several years and several times.
But the Australians have been saying, I'm going to take a small sample, and we're going to do this sort of non-informative error exchange, matrix to adjuster analysis, which seems pretty naive as well. So,
well, I'm not sure you want to go and look at some of the work. People have said, well, we can put in one parameter for all the false matches, and that's very different from anything I've seen with real-world data. Okay, and that was actually done in the original paper by Nader, Maines, and Ramanujan in 1965 in JASA. And the reason that Fritz Schern and I did our work is because we knew that matching just didn't look like that. Yeah.
It's worth pointing out that Tancredi and Liceo stuff also makes some quite strong assumptions of that kind, symmetry assumptions, that again could be very questionable. So if you're going to get anywhere with these complex models, you've got to start making some pretty strong assumptions. So I would exercise a little bit of caution about that Tancredi-Liceo work. It's very interesting, but it does make a lot of quite strong assumptions along the way.
I agree with you. There's something, and this is in fairness to Tancredi and Liceo, they aren't in a place where they can get assistance on speeding up their computation. And for those of you that are familiar with census data, you know blocks aren't very big. And at least initially when I talked to Tancredi, he said that their computation was taking about 24 hours per block. In the United States, we have 8 million blocks. Okay? You want to speed up the we think about all the analyses we've done over the years. I mean, you do a SAS analysis, if it could be 10 times faster, you'd understand things better and do better quality work, but we can't always do that.
Maybe just to clarify, since they're not here, they currently have a version that's working that is much faster per block. So from their 2013 paper to whatever they're working on now.
Well, December 2015 is the Statistica paper.
So from that, they have a version that's working with regression with linked and duplicated data that I think takes about 10 minutes per block because it's all in C++. And Andrea wrote that.
Yeah, I believe you. I don't know if it's that. I mean, it probably is that fast. I just don't know.
I've seen it, so it's that fast.
Yeah, they're in a business school, and the deal was they don't have the type of PhD students or graduate students that want to write that type of code.
So I worked with them on this, so I've seen it. Yeah, it's much faster than it was before.
Okay, good.
Another question going back to our, that Wingley paper in survey methodology where they simulated. Probably your thoughts on that one. They basically, I guess they were able to get the M probabilities, new probabilities, the match probability, and then they generated lots and lots and lots of simulations to get a sort of average error rate. Are you familiar with that paper?
Yes. I didn't say anything about it, did I? Unfortunately, I'm not sure that's realistic because the method only works on one set of data. And I repeatedly asked them, at least 2 of the 3 authors, have you ever applied it on a second set? And there's now things that contradict that, at least with other types of data. Okay, so you can't do that type of simulation as naively as they did it.
Sean O'Brien from Duke University. When you estimate, just in your application, when you're estimating parameters specifically for each of the 500 census regions, are you doing that in a way that shares data across the regions?
No, we never
Or
did it
separately?
that way. But we really, really had a hard time doing computation in the late 80s, particularly when you had to do it for the whole census. And Yves Thibodeau and I did a lot of that parameter estimation. Yves is a PhD out of Carnegie Mellon, but he also has he later subsequently got a master's in computer science. To say that we worked and worked and worked and worked just making things faster. And there's a lot of statisticians that didn't believe that we needed to do that. Or at least, well, why would you do that? Because we produced very high quality results. We wanted them used in the decennial census. So our software was the production software for the decennial. And that was the first time anybody had done something like that. So.
One more time. Any more questions? I've got a kind of question. With regards, you mentioned lots of different challenges right from the beginning, missing data, the multiplication, all the way to error estimates. So what do you think is it worth to put in most resources with regard to improving the whole process? Is there any specific area besides making everything faster?
Right now, I'm not sure that much needs to be done with the data preparation. There's a lot of things, just the knowledge needs to be disseminated to other people. The basic parameter estimation, I don't think anything needs to be done either. The trouble is, if you don't combine your standardization in just the right way in the data preparation, you can't do the parameter estimation. It took us about 10 years to figure that out. We figured it out right away, but we had so many low quality things. So this last problem about adjusting statistical analyses for linkage error is the main problem. And at least I think there's several groups around the world that will be looking at that or are looking at it. Okay.
When you're talking about the speed for how long all the computation takes, how much of it is that for parameter estimation versus everything else before you get to?
With record linkage, the main thing is comparison and retrieval. Compares across two big data sets. So that's where all your speed up is. So the big match essentially took what we had in 1990, and when our decennial area initially looked at it, all the weights were the same. Because we knew it was high quality what we did in 90, but we just couldn't do things as fast as what we need to do in the future. And so all of it is bringing things together very, very rapidly and doing the comparisons very rapidly.
Parameter estimation part's just kind of trivial.
If you structure your input data correctly. But the trouble is, what I'll mention, there's the Lahari it's the Larson and Rubin paper in JASA in 2001. At least 2 or 3 groups over the last three or subsequent years have tried to do that, and they couldn't do it. And the problem is, it takes a lot of skill with the name and address standardization in the data structuring to set things up right to go into these models. That's just for parameter estimation. Now, if you're familiar with that, you can do it just like that. And if you aren't familiar, and to give you an instance, we got our parameter estimation stuff pretty rapidly, but with the name and address standardization, we had a group of close to 15 people that worked on that between 1984 and the summer of 94. And that's at the point when we had the new generalized software and we thought everything was solved. It took us that long. Now, we were doing lots of things, so it wasn't that we just worked on those, but most of our improvement was due to name standardization, address standardization, and the better structuring going into the parameter estimation. Way in the back.
I'm Hetong, and I was going to say, so since since you said that the standardization or harmonization of the data is so important, could you share more about? I mean, is that just you get to know your data and figure it out, or I mean that seems to be the core.
The easiest way to look at it, and I was fortunate to work for a number of years with very, very good programmers. We would do printouts by what's called decreasing matching weight. And you could look at things and you could see as additional typographical error and missing data occurred, the matching weights would slowly go down. And they could look at things and say, wait a minute, how'd this happen? And after a couple of years, it was always due to the name or address standardization. So what would happen is you have a failure in those. It's like a catastrophic error because the thing is no longer a high match or a somewhat good match. It goes all the way down into the non-match region. Yeah.
Can you talk about when, with standardization, one might be over-standardizing? I mean, you think about different ways that people spell names, and you could over-clean them and you lose useful variation.
We'll get some corroboration maybe from a couple people in the room, but there's a paper in, I don't quite remember the name, it appeared 2 or 3 years ago, and they claimed that the standardization actually hurt.
That was Randall, right?
That was our group, yeah.
Okay, well here's the deal. If you go into that, almost all the problem was to do what was called nickname standardization. 100% as far as I could tell. And what we observed early on back in the 80s, that if you mess up your nickname standardization, it can do catastrophic errors. So we've never done that. And I could observe it right away because I've taken it out of a couple of the systems that we tried to develop, and people thought, well, we need these great big nickname tables. And here's where you get in trouble. You have a name like Bobby, B-O-B-B-I-E, and it's actually a woman's name from Roberta, could be a nickname, or it actually could be her legal name. And if you change it to Robert, and that's the kind of stuff that was happening, it's a catastrophic error.
That was the one. The nicknames was the one that actually decreased it. So the usual stuff you do, taking out some punctuation.
Well, they actually showed in the paper all these things helped, and all of a sudden, at the end, it was worse. And it was the nickname standardizer, okay? So the rule is you got to be you have to understand your stuff well enough not to put that stuff in just willy-nilly.
So how do you deal with this increasingly multicultural societies? Maybe that's something you're going to talk about. Are you?
A little bit, yeah.
Okay, then
We'll morph into whatever.
That's my questions to you in an hour. So let's thank Bill again for a fantastic presentation.
Thank you.